Hmm. Uh, so let's begin our journey this afternoon. Today we're gonna start our journey on chapter 4, the circuit theorems. In this chapter, we're gonna talk about several theorems and very useful for analyzing linear systems. Uh, the superposition theorem. And in second section, we're gonna introduce you the substitution theorem. And in the third section, we're gonna talk about the Devenant theorem, the Norton theorem. Those two looks very similar, but which the one is concentrated on concentrated voltage. And in section 4, we're going to talk about the maximum power transmission theorem. It's about how to maximize the power you transmit. Oh my God. And in section 5, we're going to talk about the Telegon theorem. And in section 6, we're going to talk about the reciprocity theorem. And in section 7, we're going to talk about the duality principle. Using this duality principle, we can easily understand the Devenant theorem and the Norton theorem. Those are due to each other, and also we can understand this section 6 more deeply if we understand the section 7. So we're gonna do it step by step. In this chapter, we should master this content and to which extent we should apply this theorem and how to apply this theorem in analyzing circuits. So I think first we're going to talk about the superposition theorem. Superposition is a nature or characteristic, especially useful for linear systems. So we know that a linear system must have this feature. Otherwise, it's not a linear system. It's called a nonlinear system. So in our study, since we are mainly dealing with the linear system, so almost all the circuits in the former half of this course could apply this kind of a theorem. So this superposition theorem is very useful, especially in those easy cases, circuits. So this theorem tells us in a linear circuit, the current branch can be regarded the algebraic of currents voltage independent power supply acts on circuit as own. So it's too long, but it's very simple. For example, since we have a circuit and it can voltage source and one current source, and is equals to the value of the current of the current source. And in the second branch and the third branch, which has a branch of a branch current of I2, and we know that if we want to get the number, the value of the current I2 and I3, normally we will apply our KCL and KVL equations, and by solving those equations, we can reach the conclusion. But from this superposition theorem, we have another conclusion. So if we divide this circuit, and only contain one independent source, and we can calculate the current on branch 2 and branch 3 in all these cases, and we combine all the results together. If we divide this circuit into three circuits, and each circuit only contains one of these three sources, and then we can calculate its corresponding branch current I2 and I3, and then we could add up all those three divided circuit branch current together, and we reach the combined I2 and I3, and it is identical to the original circuit, which contains three sources. So let's see. Since we have this kind of circuit and with three branches and one node, one independent node, two nodes, and one independent node. Let's see. We can apply node method we learned this morning for this node, since we only have one independent node, and itself conductance is G2 plus G3, and since there's only one independent node, so there's no cross conductance, and we can from the branch 1, we see the current comes in is IS1 here, and those two other branch which contains the voltage source could be transformed into, let's see, this G2. This is for the middle branch. And for the third branch, we can also apply this kind of a transformation. So still, we can have the current source coming to node 1 from the second branch is G2US2. And similarly, we can do it on the third branch, which is G3US3. So apply this node method, we have the relationship between the voltage of the node UN1 and the corresponding relationship between the current source and the voltage source. So since we have gained this formula, we can move T2 plus T3 and move it to the right side, right? So we don't have G2, G3 on the left side. So we have this kind of stuff, and we rewrite it here, right? And we can see they all have the same bottom, and this one is from the second branch, this one is from the third branch, and this one is from the first branch. So it contains those three individuals, right? So we can divide this. We can see that the first factor one be expressed as A1 and 1, and is corresponding to node voltage UN1 1. And the second one could be expressed as that's a little bit different. The consequences not as pleasant as we want. Doesn't matter, we just rearrange it. No, it's not like this. It's still. So we can see that the first part is like this, corresponding to this, and we can rename it as UN1 1. And the second one, from the second branch, we give it a name UN1 2. And the third one, from the third branch, we give it a name UN1 3. Look, there's three sources, IS1, US2, US3. All sources are represented in these factors. So we can see that UN1 is made up of three sub UN1. And it works like as if there's only one source acting on the circuit alone. And we can see the I2, we also could use this stuff to express it. So we also could express it into three categories, I21, I22, I23. And also to I3. We can just divide it into three parts, I2, I32, I31, I32, I33. And this UN1 1 and I2 1 1 and I3 1, those three, all under the influence of so and 1 2 and I2 and I3 are under the influence of second and third. Three this one, right? So we could do that. We know that the node voltage and the branch current are both the linear function of each they could be regarded as the superposition of the response translated each independent power supply alone. So it's quite confusing. It's a little confusing, but we will just we will cover that. It's not that very. First, first, this theorem is only applicable applied to linear. So if your circuits we cannot do that again. So nonlinear components in your circuits, we better change an idea to use some other to do so. And when one power supply works, we set the rest of the other sources to zero, which is when one power supply works if the rest sources is voltage source, we just short circuited it, and if the rest sources is current source, we just open circuited it, right? Current source open circuited, voltage source short circuited. So we only left one power supply to dance, and in the meantime, all the other power supply rests, right? So let's take example. Let's take an example. So we now know that the theorem we learn and the stuff we learn is getting much more complex, more and more complex. So we better catch up. Otherwise, we're probably not going to be able to understand it. So it's not our course is not very difficult to understand, but it introduced a lot more of a knowledge point, so scattered, and so total amount is not a small number. So I recommend that we should do some homework about ourselves, do the text. I in the book I give you. So let's see. Still, we have this circuit which contains three branches, each branch with a independent source. So when those three power sources work together, we have we could solve and we could solve the number of the corresponding I2, I3 of the branch current and the corresponding U, the voltage on each branch. But it could be divided into three sub circuits. So let's see. The first one, only IS1 works, and we short-circuited the US2 and the US3. So we leave G2 and G3 here, and we short-circuited those two. This is the first one. The other one, we open-circuited the first branch, and we short-circuited US3, only leave US2 here. And the third one, we only leave US3 here and short-circuited US2 and open-circuited the IS1. So in this course, we divide this circuit into three sub-circuit, and we can calculate the corresponding I2 under three cases. So we calculate three simple circuits, and we can have this is corresponding I2 1, I3 1, I2 2, I3 2, and I2 2, I2 3, I3 3. And when we want to have the final I2, we can just have this I2 equals to I2, 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 I2 1, I2 2, I2 3. So once we solved those three simple circuits, and we have the branch current on under each case, and we add them up together, we will reach the original I2 and the original I3. Because this is a linear system, so it satisfies the superposition theorem. So we could divide it into three simple three simple circuits. But do remember that we could apply this superposition on the current and all the voltage, but we can not apply this superposition stuff to the power. So since the power is a combination, the product of the current and voltage. So it's the quadratic function of the power supply. So it is not a linear stuff. So we cannot apply this stuff. So see P1 P2 P21 然后 P22 then P22 and then we have a P33 P23 and P2 on the G2 on G2 P2 on G2 is not equal to P2 1 P2 is not equal. So to remember that, only the current and the voltage could apply this because they are linear. They are the linear function of the voltage, the source. So they are the linear response of the to the source. And to remember, we have to be careful of the reference direction of each component. And when we apply, when we superimpose the U and I, if we have a circuit that contains the control source, we still could apply this theorem, but we should keep the control source all the way through the calculation. So if we divide, for example, still see that see if we have a control source like this. When you divide this circuit into three circuits, still the control source should be in every sub-circuit. So then you can calculate its corresponding number of the current and the voltage. So this is what we should be careful of. So to remember to take to look carefully about the reference direction when we apply this theorem. And we should always keep the control source in. We could not treat it the independent source. So linear source cannot be excluded from the sub diagram. So how to apply this superposition theorem? We could use this to calculate the current and the power of the voltage source. For example, since if we have this this circuit, and we would like to calculate I and this power. We know that P equals to 7 times I, right? U is 7 volts, already know. And I should be calculated. So since we have two independent sources here, so we can just transform it into, divide it into two sub circuits. The first one, we short-circuited the voltage source here. So it's only a wire here. And the other one, we see that we just open-circuited the first branch. The current source is gone, so the first branch is gone. So from the first one, we see that those two are connected with a wire. So let's see if there's any voltage on it. So we see that the proportion from this branch full to branch full and the second branch 10 ohm and 5 ohm branch. So they're identical. So we know that there must be no current running through. So nothing runs through this wire. So we can see that from I11 is 0. And the other one is simple. We see that I22 could be calculated into two branches combined together. One is from the lower branch, this one, and the other one is from the upper branch. So we know that 70 volts over 2 plus 5 equals to 10. And 70 volts over 4 plus 10 ohm equals to 5. So I22 equals to 5 plus 10 equals to 15. So we can combine those two, I2, I1 and I2. I equals to I1 plus I2. Since I1 is 0, I2 is 15, the total current is 15. And the power, we see that the power we already said that power equals to 70 times I for this voltage source. So it's 70 times 15, right? Let's take another example. Let's see. See if we have this kind of a circuit which contains two voltage source, two current source, right? And we would like to know the voltage of the 3 ampere current source. So it's very easy to think of that, right? We have to divide this stuff, right, into several sum diagram. Since this is a linear system, so we can use we can apply this superposition theorem. Otherwise, you can still directly using KCL and KVL and the node voltage and the branch current method as you wish. Since we have 1, 2, 3, 4, 5 branches, right? V equals to 5 and 1, 2, 3, 3. So if you would like to solve it using the traditional way, we definitely going to choose the node voltage method, right? Otherwise, you can just use other message, other stuff we skills we have introduced, like the loop current and the mesh current method. Both are all right. So you can solve this problem with many equivalent skills and methods. So which method you pick is up to you. But since we are illustrating the superposition theorem, so we just gonna use this trick to do the work. Okay, so we can just divide it. So first is when 3 ampere voltage source works, and we just remove all the other sources. We just short circuited the 6 ampere and 12 ampere voltage source. So there's no voltage source in the first and second branch. And we cut the 2 ampere branch. So since we would like to have the 3 ampere current source work alone, and we can have another subdiagram. You see that we can just leave all those three here together, and instead of doing it one by one, we can do it together. It's it's also right, and we can solve this problem here. And it's very easy to solve the second one. You see, since this this part is open circuited, so there's no current running through it, and so all the 2 ampere current running through this 1 ohm resistor, and its voltage must be 2 times 1 is 2 volts. So this part is 2 volts. And also we can see that we have this stuff here, and we have a 9 ohm 6 plus 3 is 9 ohm resistor. So the total resistance in this loop is 9, and the total voltage the total voltage on it is 18 over 9 is 2. So we know the current on it is 2. So we know that the voltage on this stuff, 3 ohm, is 2. So we can calculate that so only have 6 left. So we can calculate U2 2. And the first one is very simple, you see. We know that it's a 3 ampere voltage source. So, and this branch is 6 ohm, this branch is 3 ohm. So, definitely this one, uh, and this one is 1 ampere running. And we see that the voltage on it is, this one is 3 times 2 is 6 volts, and this one is 2 volts. So the total voltage on the current source must be 8 volts, right? Right? Oh, I was wrong. This one is not 2 ampere. It is 3 times 3 plus 6 volts is 8 volts. I made a mistake. The sphere is 3 ampere again. I just lost this omitted this first branch. So the total volts on this resistor 1 is 3 volts, and this one is 6 volts. So together they will form 9 volts here. And since we have the 6 and 3 equivalent to this 6 and 3, so we know this I2 is equals to 2 ampere, and this part is 2 ampere. And we can calculate that since this 2 ampere times 3 ohm is 6 volts, and its direction is different from the 12 volts. And also we see that this stuff has 6 ohm and 2 ampere volts, so it has 6 times 2 is 12. So we can directly using this skill to calculate that U2 X2 is 8 volts. right? So uh, so we divide this original circuit into two sub-circuits. The first one contains the 3 ampere current source, and the other one contains all three sources left behind. So we can combine those two and calculate those more easy, much more simple circuits, and we add the current back together, and we can just have the original we have the original result. So by calculating U1 and U2 separately, so and then combine them together, we have the final result. But obviously, we can do it another way, right? We can transform this stuff, and much more easy way to do it is also could be like this. Mm. Much easy way to do it with just see that we transform this stuff. It's a 6 ohm and with a current source. 6 over 6 is 1 ampere. This is the first branch. And in the second branch, we could just it's 12 over 3 is 4 ampere. And we have 3 ohm stuff here. So we can using the equivalent voltage source and current source transformation, we can transform this stuff into this kind of stuff, right? And together we have this kind of stuff. Then it's very easy to calculate, and we can combine those two together, right? This is a 5 ampere, right? And we can combine those two resistor, right? Right. So we can simply replace with a 2 ohm resistor, right? So this is a much more easy case to solve, right? Much easy to solve that we know that we can still divide this into two categories. First one with those two, and we don't have those two branches, right? And then we know that oh, well, I made a mistake. The direction of this is this stuff, so this direction is obviously is not correct. Okay, so which means our calculation, the first one is 1 ampere, the second one is 4 ampere, and the second one is going up, and the first one Uh, right. So I made a mistake. No, that's right. That is correct. So, so up, four goes up, and three goes in, right? Uh, one goes in. Oh my God, I made a bad calculation. Four and four goes in. One goes up, and this one is four, right? And we can combine them together with three. Yes, with three left. So we have. Hmm? That's it. So we can subdivide this equivalent circuit into two categories, into two sub circuit. One is contains the 3 ampere current source. The other one is without it. So that's going to be much more easier to do so. So this example illustrates that we can combine all the skill we have learned and to achieve the same result. So, but if you don't remember this trick, you still can using the current source and the mesh current source, the loop current method and the mesh current method, and if you even if you don't remember those stuff, you still can apply the traditional KCL and KVL method to list the equations and solve it step by step. But it's only a little bit complex, much more complex. So this is it. This is this example. So we have to pay attention that how you superposition how you choose the superposition sub diagram is random. You can just uh, if you have n independent source in your circuit, you can divide it into n sub circuits, or you can just pick some several uh, leave some independent source in one diagram and leave the rest in the other diagram. And or you can continue to subdivide the sources, the circuits into even smaller sub circuits. So it's all up to you. So it's very flexible to do so. So let's take a 10 minutes break. Let's continue our journey. Could you understand? Could you hear me? Okay, let's continue. So from the last two examples, we have already learned how to and when to apply this kind of a theorem. But if you don't understand it, it doesn't matter. But it's not very hard to understand. So you go back to check this two examples again. Then we have master this kind of stuff. It's still a trick, little trick. All these theorems and methods we learned uh, it's not only useful skills to analyze the circuits, but it's also a very useful tool, a very useful window to observe the behavior of a linear system. So we know that we can do uh, this subdivision according to our view, and you can apply some several independent source to one diagram and the rest to another diagram, and you can continue to subdivide the rest diagram. So this is how we do about it. Now we can take another example. See, in this time we have a controlled source here. This one is a voltage controlled current source, a current source controlled voltage source, and its control variable is here. It's a current of this 10 volt voltage source. So still we can apply this node voltage method. Okay, we learned this in this morning, and we can also do that. Do the current method. Apply the match current method as both are right, and it doesn't matter, right? But we could also using this kind of trick to divide this diagram into two parts, which part one contains only this 10 volts voltage source and the control source, and part two contains this current source and the control source. So no matter what kind of which way you divide this diagram, you have to leave the control source here in. So we can draw a sub-circuit diagram, right? One with current source off, and the other short-circuited the voltage source. So then we can calculate those two easily, and we can find the U and corresponding U, U1, U2, and U2. But have to keep the controls in, otherwise reach the same conclusion. So we see that the first the diagram that is very simple, right? Because it only contains one. It only contains one. So we only have to consider this, right? So the voltage of this two 2I1 and have a voltage of 2I1. And this one is I1, 1I1, right? So they combine is 5I1. 5I1 equals to but we see that those two are in a different position. So we know that this one is in the opposite direction with the reference direction. So let's see. I1 equals to 10, 2I1 and divided by 2 and 1. So we know that in this loop, the total resistance is 2 plus 1. And since the voltage of 10 volt current voltage source is referenced in the opposite direction with this control source, so we take we give it the control source a negative sign ahead of it. So we could calculate this this stuff is 5 is 2 for the first one, and the first U1 is 1I1 plus 2I1. I1 is 2I1, and so is 3 times 2 is 6 volt. And for the second subdiagram, we see that it's very calculate this stuff. And we can have this conclusion that anyway, since this second diagram is very simple, you can use even using the traditional loop current method to solve it. All right, it's so simple. So we don't talk about that too much. And you still can use the corresponding not voltage method to do it. So still, you can easily solve this I2. Combine them together, right? X2, X2. 2 amp -1 ampere. So from this case, we know how to deal with the branches that contains control source. We still could apply this superposition stuff method, and only this time, no matter what kind of subdiagram you create, each one must be the control with it, and we can still do the calculation as usual. So let's take another example. See, is passive network like this, and we put a current source to it and a voltage source to it. 1 volt, and S equals to 1. We can measure a current here. Voltage source here. S here, and we have a 1 ampere I here. So the question is, if we put -3 volt US here and 5 amp Is here. So what is the response of the current I? So this is a very typical. We're dealing with an experimental method for studying the relationship between the excitation and response. So if you have a network which is very uh, complex and we don't know what happens inside, know what is what's the behavior of it. When we add some stimuli onto it. So this time we put two stimuli. One is the current, the other one is a voltage source. By we can get the result from two equations, and we can have the result of the third one. So let's see. We could consider this as a network of storage components, and it doesn't. Definition is. And wait, this we separate in the other one is quality source only. So you can see the current I is the response of two sources. So it contains K1 I and K2 U. S equals to 1, S equals to 1. So we have this K1 plus K2 equals we're substituting a second group of experiment data, and we can have this stuff, this equation. So two unknown variables and two equations, so we can solve it, and then we can reach the conclusion that K1 equals to 1, K2 equals 2. So which means I equals to IS plus US. And we put the data from the third experiment here, and we can reach the conclusion, right? So this example gives us very interesting result that sometimes you don't even have to solve. We don't even have to. We don't even have to know what's inside a network. We still could have the right result on the particular port of the passive. So this is a very good nature of a linear system, and if we could harvest it rightly, we can save a lot of labor analyzing it. So this is the superposition stuff theorem. Then we can talk about the homogeneity principle. So which means in a linear system, when all the stimuli augmented or increase or decrease the same fold, and the corresponding response could be a voltage or could be a current, will increase or decrease the same amount of folds. So so we increase all the stimuli in the system by two folds, and the corresponding response will increase or decrease two folds according to the tendency of your stimuli. So this is another good nature of a linear system. So we could harvest this feature and apply it to analyze the linear system when it's necessary. So we must be aware that if there's only one stimuli or one excitation, the response is proportional to the excitation. And if we have several independent sources and they are not augmenting the same fold, the corresponding results will be the results of the response will be the corresponding response times its corresponding force according to that specific stimuli. So we can see it in our examples. So it still have the ability of the superposition theorem requires. So we have that activity. For example, see we have a circuit look like this, right? And what we would like to know the value of the current I here in this branch. And we know that this stuff is 2 ohm, right? And R1 is 1 ohm. R1 is 1 ohm. R2 is 1 ohm. And US is 51 volts, right? And we would like to calculate the current. Originally, we could just using the node voltage method or the loop current method to calculate the current, right? But that is not what we're going to do. If we want to, that is too complex to use the traditional way. Since we have already learned about this new theory we would apply this homogeneity principle to avoid complex calculation. So, see, since we have a branch current I here, and its the resistance in this loop is 2 times of this one, so which means that the current since those two branches have the same, you see that, and this one, they share the same voltage. So which means you see that this one is 2 ohm, this one is 1 ohm. So if the branch current in the RL branch is I, so in this branch it must be Ri 2 times I. And see, this one is 1 ohm, and we see that this node have 3I current goes out, so this one must have a 3I current goes in, right? And we also know that R1, R2 is 1 ohm, so this one is 1 ohm, R1 is 1 ohm, this one is 1 ohm, this one is 1 ohm, right? So this one is 3I, and the voltage of it is 3I times R1 plus I times 2I. So the current, the voltage between this, right? The voltage between this node and this node must be 3I times 1 ohm plus 2 ohm times 1I is 5I. So 5I is 5I volts as is at to this node. Let's call it node 1 and the ground. We call this the ground. So we see that there's 5I voltage on R2, so it must have a current of 5I over 1 ohm, so it's 5I. And since there's 5I goes out node 1, 3I goes out node 1, so it must be 8I here, go through it, right? And still can calculate the corresponding voltage between this part and this part. So it must be 8I times 1 plus 5I times 1. So it must be 13I. And 13I over this R2, it must be 13I. Right? And 13I over it, and must be 21I goes in. And 21I plus 13I here, we can do this kind of calculation of ourselves, right? Or we can do it another way. We just don't like this taking the calculation with this I and longer, right? Let's see. So we can just assume I dot to be 1 ampere, and from the relationship between all those resistance, we know that this one is 2, this one is 1. So it must contain 2 ampere, right? Right. And we also know that R1 goes through 3 ampere, right? So it's 3 volts. So it must be 5 ampere goes through R2. Still, 3 out, 5 out, and this must be 8, right? 8 volt, 5 volt. This must be 13. 13 volt, 13 ampere, and 8 ampere. We must be 21, right? So now we have 21 in total, right? And it's 21 volts. And the combined the combined, let's talk about the first loop. And we add all the voltage on three components together, and it must be equal to 0. So the US must be equal to 34 volts to satisfy this assumption that I dot is 1 and I dot is the number we assumed in this branch. So obviously it's not identical to the US equals to 50 volts. So it got some proportion. So the real I must be filling the same proportion that the US dot and the US have. So I is the same proportion to I dot, similar to same to the proportion between US and US dot. And since US is 151, US dot we calculated is 34 volt, and the I dot we assumed is 1, so we can reach the final conclusion that I equals to 1.5 ampere. So this is very cunning trick to do so, right? Instead of list the equations from the traditional way that the mesh current or loop current or the node voltage or the traditional KCL, KVL stuff. When using the relationship between the current and voltage of parallel and series connection resistors from the knowledge we have learned from the previous 2 weeks, right? So this is very useful. So this is a very good demonstration of how to apply this kind of a principle. So so that means that we have several tools to solve one single circuit problems. So all these examples are how to apply this kind of a simple DC circuit, which is linear and it's very simple, right? Although it looks very complex, but it's not very complex. Especially, we deliberately set the proportion of the resistance to say then so we could gain a nice result. But if the resistance is different, we still could apply this kind of method to do this trick. Although the final result could not be that succinct, right? But still, we could apply this kind of a method. So in this case, we have learned, we have used our very, very tiny little skills of the series connection on the parallel connection, and its inner relationship of this voltage and current. So this is how we apply this stuff. So I think, could you follow? Do you follow? So I think this is not very a difficult one, right? So by calculating the corresponding voltage between those two nodes, and we can calculate this stuff step by step. Instead of calculating full mesh current, we only calculate one, and we just find the constraint between the voltage source voltage and the current in this loop. So this is a very, very cunning trick to solve this example. Then we can introduce you the substitution theorem, right? This is another good behavior of the linear system. So, so far we have learned many useful skills and useful tools to solve problems. So let's see what is a substitution theorem for any given circuit. If one branch current is IK, and for the case branch, its current is IK, its voltage is UK, then we can replace this branch with a independent current source whose current equals to IK, or we can replace it with an independent voltage source which whose voltage is UK. Or we can just replace it with a resistor with a value of resistance equals to UK over IK. And once we did this substitution and the altered, the replaced circuit, all the current and the voltage in their branch will stay the same. So, which means the solution is unique. See, we have a branch like this, and it has the voltage of UK and the current of IK. And we can replace it with a voltage source, independent voltage source with UK. And we can replace it with a current source with IK, both are right. And we can even replace it with a resistor, R equals to UK over IK. So let's try to prove this theorem. See, we have this network A and a branch K, and the branch K has a current of a current of IK and a voltage of UK, and we replace it with a voltage source UK, and we can see that if we put this branch spike into this stuff, we can combine them together, and we put a negative UK here, and we see that right, the total voltage of this branch will not change, and the total current of it will not change, right? And we just short-circuited this branch because it contributes no extra UK voltage to the branch, right? So we just remove this part, right? We remove this part. And we can just short-circuit it. So to the network A, it does not see any difference. Still, its voltage is still UK, right? And current is still IK, right? So which means that we will follow. I don't know. Are you following? Let's see if we have a branch like this, okay, right? And we put two current source, voltage source, and head to head. So together they will contribute nothing, right? Those two will counter effect of each other, right? So it will behave like this, original one, right? Because those two counter effect each other, and now we just remove this part, right? We just bypass it since the current, the voltage on this branch is equal to 0, right? Those two with total branch with contribute the night voltage of 0, so we can just bypass it, right? And let the current IK run through. So we see that we can replace this stuff with a current voltage source of UK. So now we can apply this theorem to solve this problem. Let's see if we would and we have a independent voltage source. Now, how could we calculate that? Of course, we can use the trick that we have learned this morning, the node voltage method, and we could also apply this the parallel connection of the resistance and of resistors and the series connection of resistors to do the trick, right? And we could also transform this stuff, right? Let's see, this is a typical Y-shaped or T-shaped resistance resistor connection. We can change it to a Y-shaped or delta-shaped resistance, right? And we can also do the trick to this part, right? This is a delta-shaped resistance resistors. So there are so many tricks we can do. But today we're gonna try another new way, right? See, I1 equals to the voltage over the total resistance, and we know that this the 5 ohm and 10 ohm they are in series connection, so and they are parallel to the 10, and those three is in series connection with this 5. So we can calculate the total resistance, and we divide the 110 volts with this resistance, and we can calculate the I1, right? And we know that I1 equals to 3 times I1 over 5, right? And so it's I2 is 6, right? Because the distribution of the resistance that is this stuff has 10 and this stuff is uh, 12, so is 15. So in total, they will share the 3/5 of the total current. So I2 is 3/5 of the I1, right? So it's 6 ampere. So what is left is I3 is 10 minus 6 is 4. And the voltage is I2 times 10 ohm is 60 volt. And we can just replaces, right? We replace this branch resistance with a resistor with a voltage source, and still we have a current I2. Since if we replace it with a 60 volt voltage source, let's see, I1 is still 110 minus 60 is still, let's see, this is 10 60 volts. And I1 is the same, right? And let's calculate I3. I3 is still the same stuff. We see that it's 60 over 15 is still 4. So its direction and the value is not changed. So we didn't change the value of the I1 and I3, and also their direction remained the same. So once we do this kind of a replacement, the voltage and the current of each branch will not be altered. So they stay untouched. But it only works for this kind of a DC circuit, right? Which means this DC circuit, its value is constant. So it does not float with, does not dance with the time. So, but if we're dealing with a dynamic circuit, this kind of a substitution method will not stand any longer, right? So be careful of the situation that we could apply this trick. So all the trick we could apply that require some prepositions, like the mesh current method. It could only apply to the planar circuit, which is a two-dimensional. And if we're dealing with a three-dimensional circuit, which that we cannot apply this mesh current method any longer, we could do the corresponding altered form of that, but we could not using this original form of the mesh current method to apply it to the three-dimensional circuit. So this is a very interesting theorem, right? Very interesting. So we see now, we see that in our course, is the tricks we have is not very complex, and but we have many tricks. So it does need some time, put some effort to memorize it and to digest it. So if we don't review all the contents we have learned, we're probably gonna forget about that. So in order not to forget about that, we have to go over it of yourself after the course. Let's see the reason why the corresponding will stay the same after we do that replacement. It's just because the KCL and KVL constraint relationship between the branches and the sources is not changed. So the corresponding relationship of the voltage and the current will not change. So if current will not change. All this change from the relationship of KCL and KVL. From KCL and KVL laws, this conclusion. They are indirect from the KCL constraint and Ohm's law and other like that. So we now know that we still know that uh, uh, if it is the nonlinear system is working in a dynamic state, this stuff will not work. So we have to pay attention to the scenario we could apply this kind of stuff in the scenarios that we could not apply. And the second stuff we have to memorize is that after the substitution, after replacement, all the other parameters on other branches should not be touched. So we don't change any other stuff. Uh, Current source. We can replace the 5 ohm resistance like this. Now the question is, will this stuff behave just like the original one? See, that is the question, right? And from the previous lesson, we have learned that if you have two parallel identical what is source, you right? But the current, you see that after this stuff, if you have a loop without voltage source and if you have no current source node, in this case, you see that we do not the current distribution in this branch, right? So it could be 3 to 1, and it could be 5 and 0. And no, so the in this case, the distribution between the replacement we cannot be sure. So we have to pay attention. If we encounter this kind of a situation, we're probably not gonna do this randomly. So much for today. Let's continue our journey next week. See you next week. Class dismissed. Class is over, guys. Are you sleeping?
Okay, teacher.
See you next week.
Okay. Bye bye.